If one wants to make progress in mathematics, one should study the masters and not the pupils. I let these words guide me in my mathematical journey. One of the first works of a master in mathematics that I read was Cauchy's Cours d'analyse. In this book, I stumbled on a hidden gem, a very beautiful way of defining functions, namely via functional equations. A new way of defining functions enables us to give beautiful new proofs, which are often very simple due to the simplicity of the functional equation. The functional equation that really hooked me in Cours d'analyse was one of D'Alembert. This is D'Alembert's functional equation. Assuming f is continuous, its solution is either cosine or the hyperbolic cosine, or the constant functions 1 or 0. D'Alembert's functional equation shows how similar the hyperbolic cosine really is to the cosine. Furthermore, it is a very simple way of defining the cosine elementary and without reference to geometry. But this was not the only functional equation Cauchy treated. Cauchy treated 4 additional, much simpler equations. We will choose one of these simple equations in order to show how functional equations determine a function, assuming continuity. Our proof will illustrate the importance of this extra assumption of continuity. Let's find out which functions omit this functional equation. Our plan is first to determine its values for the natural numbers. Then, pretty analogously, we can find its values for all positive rational numbers. Using the functional equation again, we will also be able to determine the value of this function for negative the numbers we already had, that is, for all rational numbers. Only by our assumption of continuity, we are then able to extend this definition to all real values. First, we start at f1, called a. f2 can then be determined as follows. 2 is 1 plus 1, so we can use the functional equation in order to show f2 is a squared. And 3 is 2 plus 1, so we can apply the functional equation and use that we knew f2. Repeating this, we can show f of n is equal to a to the n. We can now already guess the solution, but we want to show that this is the only solution. Instead of splitting a number into ones, we can split 1 into fractions. Using the functional equation again, we get an equation for f of 1 over m. Solving gives that f of 1 over m is a to the 1 over m. However, we can only take all roots if f1 was positive. Luckily, we can use a trick to show that this is the case. Namely, split x in 2 equal fractions. The functional equation then shows that f of x is equal to a square, so f is positive. Therefore, we can take the mth roots. By replacing 1 by n, we can even determine f for all fractions n over m. That is, we can determine f for all positive rational numbers. In order to determine f for any rational number, we need to determine the negative values. Let's introduce negative x by subtracting x from x and use the functional equation. Solving this equation for f of minus x shows that we can determine f for negative values if we only knew f of 0. To determine f of 0, we will look at the fundamental property of 0. The fundamental property is that x plus 0 stays x. Applying the functional equation to this identity gives the following. We can only divide by f of x if there is an x such that f of x is not 0. F everywhere 0 is a solution to the functional equation, but if it's not 0 everywhere, we can conclude f of 0 is 1. So we can determine the value of f for any negative rational number. We have now determined f for all rational numbers. Without any additional assumptions, we cannot extend this function any further. There lies the importance of our additional assumption of continuity. In order to visualize the extension from the rational numbers to the reals, let's take a look at the graph of our function. The rational numbers q are dense in the real numbers r. In order to illustrate what this means, start at the whole numbers. Then divide the gaps in half by adding multiples of 1 over 2. Repeating this process, we can make the gaps arbitrarily small. We did not even use all rational numbers, but only a subset called the dyadic numbers. So any real number can be approached by dyadic and therefore rational numbers. This is what it means to be dense in R. There are multiple ways to define continuity. One way to define continuity informally is as follows. A function is continuous if approaching a certain input value corresponds to approaching a certain output value. Since we can approach each real number by rational numbers, we can determine each value of f of a real number. In fact, a to the x is actually being defined by continuously extending it from its rational values. So now we show that a to the x is the only solution to the functional equation. Our solution to the functional equation illustrated the general way of finding and proving solutions to functional equations. The values of f of 1 and 0 are fundamental. From these, we can determine the values of all rational numbers. Then we need to use our continuity assumption to extend it to the reals. In the next videos, we will see some applications of functional equations, so stay tuned.